got slideshow set up from current slide. All right. Before we get going on this, it may be a little hard to see the board with that bright sun coming in. But after the last 2 days of rain, that's sort of nice to see. But we needed the rain badly. Before I get going on today's lecture, though, I wanted to say this, okay? One major announcement, and please do it, okay? The student course evaluations are now open. You can do the student course evaluations for any course and everything you've done this fall, this term. So, have any of you done it already? None? Please get those done. You have till the end of the term, but please, I know when I was a student, end of the term came, the memory bank just sort of cleared. So don't put it off too late so you forget to do it. So please do the student course evaluations. We value them. Okay. Any questions? Anything we've done up till now? Let's do a quick review on how things are standing. That shocked me. Hardest little projector to get to line up. Okay. Today we are going to continue in Chapter 6, Electricity and Magnetism. We'll get covered, I'm pretty sure, what we'll need for today's lab. So then we'll have the lab done for basically the Ohm's Law lab. So we'll have time for that. So we will have class up until our normal 5:45. And then we'll have lab from 5:45 to 7:45. Now, the folks that were here last time, the lab went pretty quickly. I think this time will too. Oh, I forgot one thing to tell my student to set up for the lab, so I've got to go get that. So it's not quite ready, but mostly ready to go. Except we couldn't set up on the tables because there were people in there studying. So I have to set up that once we get started on lab. But we'll have lab from 5:45 to 7:45, or until you finish it. And you probably will finish early. And then we'll move on. Next Tuesday, we will, if we don't finish the chapter today, which we probably won't, we will finish it, I think, next Tuesday. And then next Tuesday afternoon, from 5:45 to 7:45, we'll have the last lab on electricity and magnetism. Okay? Next Thursday, and probably Tuesday, we'll start Chapter 8, which is the chemistry chapter. And next Thursday, we will continue Chapter 8. And I think we'll get far enough along, I'm pretty sure we will, to have the lab on that chapter. Okay? So that leaves the last week. Okay? We probably won't finish Chapter 8 on Thursday, but we'll finish Chapter 8 on Tuesday, I think. We'll at least go as far as we go. And then at that point, your final exam is scheduled for Thursday from, and what my plans are now, if we finish the chapter on Tuesday of next week, Chapter 8, then we'll have, the final will be in two parts. The last chapter test, the Chapter 8 chapter test, and then the final exam, which is comprehensive. With the comprehensive final, I apologize to you now, it's going to be way too easy. It's matching, okay? Words and definitions and descriptions on one side, and the words on the other side, you match that. So it's a pretty straightforward test, about 20 questions, something like that, okay? So that will be the final. Now, I'm thinking, I'm not sure, but I'm thinking we probably will be finishing the chapter 8, before the end of the period on Tuesday. We don't have another lab in Chapter 8. That's it for the labs. And if any of you want to, this will be completely up to you. If you want to, you can take the Chapter 8 test on Tuesday and then take your final on Thursday if you prefer to do that. But we'll still be covering new material in 8 the beginning of Tuesday. But if you wanted to this weekend, you can work up your formula and equation sheet, over the weekend, and then, okay, I'm sorry. This is next weekend, not this coming weekend, the following weekend. And if you want to, you can take that last chapter test early. You don't have to. I'll be here Thursday, and you can take it then. However, if some of you actually want to take both the last chapter test and the final on Tuesday, I'll let you do that too. I'll have both of them ready. So if you want to take them, you can. But if not, I will be here Thursday from 3:15 until 7:45. Okay, so you can take them Thursday. So I'll give you the option of taking them early if you want, one early if you want, or both early if you want, or wait and take them both when they're scheduled on Thursday. This is the last week, not next week, but the following week. So I just want to get that out there so you'll know how to plan too. Okay, any questions? All right, let me see, one more coming in, and it's the manual. Okay. All right, then where we're starting today is in chapter 6. If you got the new edition, it's on page 147. If you have the older edition, it's under electric current, which is section 6.2. Okay? And what we're talking about, as I said, electric current is 6.2. We've talked about the electric circuit, made observations on that, and that's what we did in the lab on Tuesday. So today we'll be proceeding from this point. So what is current? Okay? Charge, measured in coulombs, or electrons, but usually in coulombs, okay? That's how much charge is moving. Current is moving charge, so it's how much charge moves per unit time. Now remember, in physics, we've been doing this all term long. We started talking about displacement. We took time rate of change of displacement, and we got speed, or velocity. Time rate of change of distance was speed. Time rate of change of velocity is acceleration. Time rate of change of momentum is force. Time rate of change of energy is power. Okay, we're always taking something per unit time. Well, for current, for charge per unit time, that's what defines current. The unit for current is either the ampere, or it's quite often we shorten that to the amps. Now notice it's given in a symbol of a capital A. Why would that be a capital A? Why would the unit amps have an abbreviation capital A? Why did Newton have an abbreviation capital N? Named after somebody. Well, Louis Ampere was the French physicist who did a lot of the early studies with current, and so they named the unit after him. Now, I don't know if you've noticed that Coulomb was French, Ampere was French, Volta was Italian, but but a lot of Frenchmen were very actively involved in science about this time. This was shortly past the French Revolution, along the time, say, of Napoleon and stuff, but the French Revolution came shortly after the American Revolution. Now, I don't know this for a fact. Someone could do a research paper on it and see, but I'm pretty sure I do know this guy who's coming in. I've seen him before somewhere. Okay? All right. James is here. Okay? But I'm guessing that these characters, Coulomb and Ampere, I'm guessing, lived about the time, say, of our American Revolution, which was around the time of the French Revolution. Okay? That was sort of a high point in France's history before the Revolution. France was sort of the cultural and, in many ways, academic center of Europe and of the known world at the time. Okay? Does anyone recall who one of our ambassadors to France was? We had several. An old guy named Benjamin Franklin. Okay? What was he famous for? Lots of things, by the way. Yes, he's one of the ones. In fact, he has been accused of being the one that decided that electrons should be negative. Okay? Let's make protons positive, electrons negative. I mean, it's just a coin toss. Who's going to do it? I've heard it said that he was the one who chose that. And of course, now then, our currents flow in the wrong direction and all that kind of stuff because it's a negative charge. But anyway, if he was ambassador to France about this time and all these French scientists were doing, I bet you they got together. And I bet you they exchanged notes. I bet you that was a very interesting dialogue and exchange between those characters. So those were some bright, bright dudes. Okay? So the units of amperes, current is charge per unit time. Here is the symbol. The symbol for current, and I don't know why, is a capital I. I do not know why they chose that symbol for current. Okay? But charge is Q, little q, capital Q we used for heat in the last chapter, chapter 4, and T, of course, little t is time. So current is charge per unit time. Q divided by T is I. Okay? Now, there's two types of current. One of these is direct current. That's what we've been using in the lab so far. That's what you use in your batteries, in your flashlights. That's what, basically, your cars are direct current machines, right? The electricity in cars, direct current. Now, you manufacture alternating current, but you have an alternator that changes it to direct current. Because your battery, your starter, your electronics, everything runs on direct current, okay, in your cars. Your cell phones, your calculators, your computers, okay? The projector, no. The projector's alternating current. The computer, though, is direct current, okay? What plugs into the wall? What are we getting out of here? No, that's alternating, okay? Well, wait, I just said my computer was direct. How could that be? A big old thing, okay? This is a AC-DC converter. AC coming in, DC going out, okay? So, alternate or direct current, the charges move basically in one direction. They bounce around, and it's not a straight line type thing, but they do move generally in one direction. Most of your electronic devices, your batteries, anything that runs on a battery is direct current, okay? Solar cells, you know, lots of things, direct current. Your alternating current, on the other hand, that's changed, the charge is constantly in auxiliary, goodness, I can't say it, oscillatory motion, okay? In other words, really the charges are just moving back and forth, back and forth, back and forth constantly. There is no net current flow in alternating current. Really what you're dealing with is the field. That's what's doing the work, the field. The field is set up and it's an alternating current. And that's what is happening there. Okay? So when we were talking before, do the electrons leave the switch and go through the bulb and turn on the light? No, they're just going back and forth like this. But the electrons here are going back and forth. All of them are going back and forth. And even up there, they're just going back and forth. Okay? Now, once they reach the capacitor, I think that has to be one direction only. Okay? We won't worry about that. Now, that was current. And by the way, I didn't say it back here. The unit for charge is, you remember what that one was? Unit for charge? I mentioned its name already. A little louder. Newton is force. Force is Newton. What's the unit for charge? No, that's current. What is the unit for charge? Mentioned his name earlier. It's not Celsius, but it uses the same symbol. words, it starts with C. Unit for charge? Anybody? Okay, when we're talking about voltage, voltage is energy per unit charge. The unit for volts is joules per second. No, that's little c, okay? That's C-A-L, calorie. That's energy, or heat energy. Charge, I mentioned his name just a few minutes ago. When I was talking about Ampere was a Frenchman, I also said Coulomb, exactly, Coulomb. That's your unit for charge. So 1 amp is 1 Coulomb per second. Charge per unit time, Coulomb per second. What's that? I don't know. It's just the symbol they use for it. But it's standard universal. I don't know. It may be that the Greek or the Latin or the, something another, maybe the French word for that they were using for charge started with Q. I don't know. I don't know how they got I for current. Okay, that makes no sense to me. Why they capitalize it, I don't know. Except little I could stand for imaginary number or the x coordinate of a plane. I don't know. Okay. So that's equation 6.4. All right. Now, this is something that's a little bizarre in your book. There's about 2 pages with almost no slide involved at all. But much of this we've already talked about. For instance, the nature of current, okay, that we covered on last time, and in fact in the lab you did something that looked a lot like figure 612 at the bottom of page 148 or thereabouts under the nature of current. Remember that? Okay. Then there was one on current mechanisms that we have also talked about. It's just sort of like the slides in the book aren't syncing too well. Okay. Then the last thing they said under current, then they talked about alternating direct and alternating current. That was the previous slide. Okay. So like I said, they're not just meshing up too well. But here's mistakes, and misunderstandings. What is electricity? Okay. It's a misunderstanding. Electricity is electrons moving through wires at nearly the speed of light. Number one, they move extraordinarily slowly, okay? And it doesn't have to be just electrons, but usually in a wire, that's what's moving. But you can read that, well worth a read, help better your understanding. Directly below that, on page 150, is electrical resistance, and that's where we're picking up here. Now, electrical resistance, okay? The name almost sounds like something is impeding the flow of electrons. And that's not a bad way to look at it, okay? But it really isn't about the flow, even though that's involved. What it is the loss of electron current energy. The energy that those electrons have, that's what's being resisted, okay? Patrick's here. Find my pen. Okay. So that's the energy. The resistance is the loss of energy. There are 2 sources of this resistance, or at least 2 we're going to talk about. Number 1, okay, and this isn't a very good picture here. In fact, it's not a picture at all. But if you turn back in your book to that picture on page 149, and we showed it earlier. Let me go back and find this one, okay? When there's no current, the charge is evenly and randomly distributed. When there is a current, in other words, you introduce an electric field by means of a battery or a power source or something like this, then the positive charges start moving that way, the negative charges move this way, except positive charges really don't move, not in a wire, okay? It's electrons that move. But they don't just move in a straight line. They go up, and this is what they're talking about there. There's two sources of this resistance. One, the electrons get in proximity to another electron, and they repel each other. So now you got to move it in the wrong direction until they slow down and move back. Secondly, because they're attracted to nuclei, because they're positively charged, they bump into nuclei along the way, and then they recoil or rebound off of that. That slows them down. So those are the two, whoops, went too far. Those are the two sources. First, they collide with other electrons in the current, and secondly, they collide with other charges in the material, meaning positive charges, nuclei. Okay? Now, the stronger the electric field, then you would think the more current flow you had, and that would be very correct. Okay? But the greater the resistance, the less current flow you got, and that would also be correct. Okay? This leads to Ohm's law. Now, Ohm was not a Frenchman. He was a German. Okay, so we had Coulomb, Ampere were French, Volta was Italian, and now we have Ohm, who is German. Georg Ohm. It looks like George, but I think they pronounce it Georg. Okay, Ohm. Now, he studied this concept of resistance. Resistance isn't as easy to measure. We can measure it, and we do measure it, but it's not as easy to measure as voltage is, or that potential difference, or current flow of charge. But he studied the concept of it, and he found out the voltage was proportional to the current proportional to the voltage, and the constant proportionality he named the resistance. So voltage, the parameter is V, unfortunately or fortunately 1. The unit is also V, volt, okay? Second? Or E, yeah. I'm used to, back when I was learning it, E is equal to IR, okay? But nowadays they're calling it V more likely, which is, the reason they did that, E is now the parameter for energy, not voltage. So, what's that? Yeah, electromotive force. That was the old term. And what was problematic with that term, it's not really a force, okay? It's a energy per unit charge, which isn't quite the same as force. It's related, but it's not the same. So they've gotten out. In fact, in the physics books that we teach from, they'll say EMF, but they won't say what that stands for because they say it's not a force. It used to mean electromotive force, but it's not. We just call it EMF now, okay? So, yeah, that's why it used to be called an E, okay? And E is equal to, or V is equal to IR, current times resistance. Now, another way to express this, and this is what I was saying earlier, current is directly proportional to the voltage with the constant proportionality being 1 over R, or current is inversely proportional to resistance with the constant proportionality being V, okay? So in other words, we don't have a separate constant, it's either voltage or resistance, whichever it is. So current, when you increase the voltage, you increase the current. When you increase the resistance, you decrease the current, okay? So current increases with voltage, decreases with resistance, okay? Now, let's look at units. What's the unit for voltage? EMF? Volts, yeah. So one has the same parameter as the unit. What's the unit? What does I stand for? Current. And what's the unit for current? Oh, that's the symbol is I. The unit is 8 amps, amperes. Named after Louis Ampere. Okay, resistance. What is symbol is R? What's its unit? Ohms, exactly. Ohm studied this. He was a big deal with it. So, usually if it's named after somebody, what would we use as a symbol? The capital letter. But guess what? If you had 5 ohms of resistance, which is not very much, by the way, if you wrote that, whoops, let me get my pen activated. Okay, if you wrote that as 5 ohms of resistance, what's wrong with that picture? Yeah, it looks like a 50. How could you tell whether it's talking about 50 something or 5 ohms? So let's not use that. Capital O, not a good idea. So they turned to the Greek alphabet. And in the Greek alphabet, the letter O in the English alphabet is related to, in the Greek alphabet, the letter in the Greek alphabet, Omicron. But guess what its symbol is? O, okay? So we didn't want to use Omicron, okay? But in the Greek alphabet, there's another letter that starts with O. It's not up there after mu and nu, O and Omicron, not that one. But at the end of the Greek alphabet, there's another letter called omega. Okay? Now, if you think about that too much, it depends on what your background is. Have you ever heard the alpha and the omega? Meaning the beginning and the end. Beginning and the end. And alpha is the first letter in the Greek alphabet. Omega, not Z or Z or anything else. That's the last letter in the Greek alphabet. So when they said from alpha to omega, that means from beginning to end. So there is another O word, O letter in the Greek alphabet, and it's omega. This is the symbol for omega. So this is the, and that's the capital omega too. The little omega doesn't look anything like that. Little lowercase omega is like this. Use that a lot in electricity too, but for something completely different. So capital omega, this symbol here, that's what we use for ohms. So 5 ohms would then not be 5 O, it would be 5 omega. Okay? So we'll erase this and put this. 5 ohms. Very good. Now, another sort of dumb story about how crazy or weird physicists are. They do some strange things sometimes. Resistance is the loss of current energy, is the stuff in a system that resists the flow of current. Resistance, that's why they call it that. Now, its reciprocal is called conductance. How easily it allows the flow of electrons, okay? And they call that conductance. So, and actually someone came up and studied this and stuff and dealt with it, so they needed a unit for conductance. Now, what would they use as a unit for a conductance? Can you think of anything that would be a legitimate unit for conductance? They didn't have somebody's name to append to it, so the physicists had to come up with some unit for conductance. Anyone want to? No, that is power. Yeah, energy per unit time. Conductance has the unit of mho. Has nothing to do with the Three Stooges either, okay? Now, why would they have named the unit of a conductance, which is the reciprocal of resistance? Why would they name it mho? Look at the spelling. It's ohm spelled backwards. Boy, physicists are strange people. It's the reciprocal of resistance, so they made it mho. Okay? Now, what symbol would they use for mho? Maybe an M? No, that's meters. Capital M? No, that stands for use a parameter for mass, or it's the prefix for mega. So no, it's not that. What would they use as the symbol for a mho? You got it. Okay? They took an omega and wrote it upside down. That's not a letter in anybody's alphabet. They just, because it's reciprocal, which is the inverse, they took it and turned it upside down. Have you used it before? You've seen it before. Okay. That is exactly true. Yeah. Okay. So that has nothing to do with the book, today's lecture, or anything else. Just a weird thing about physicists. They're strange, strange animals, aren't they? Okay. So there's Ohm's law. There's one other way to express Ohm's law. Can anyone think of it? V is equal to IR. I is equal to V over R. Or, what would be the third way? R is equal to V over I. You got it. And you can set up your triangle or your circle and use it there. In fact, that's the first place I ever saw those symbols, that technique used is Ohm's law. Okay? Good deal. Any questions on that? All right. Now, more on resistance here. Several factors, physical factors, contribute to resistance. Okay? One of these is the type of material. We've already sort of talked about that some when we were talking about conductance, when we were saying materials that were good conductors, bad conductors, and stuff like this. So sure, if a material is a lousy conductor, it has a lot of resistance. So the type of material, copper is a very different resistance from iron, okay? Because copper transmits electricity very easily. Iron has a lot of resistance to it. The second thing, though, is the length of the thing. Now, I don't know if you've ever experienced something like this before. I'll give you this sort of a dumb example. Remember we did the water wheel looking at circuits, okay, the pump model, the analogy. Well, several years ago, a few years ago, remember when we had the really bad ice storms? They had like 2 or 3 in one winter. It was maybe 3, 4, 5 years ago, something like that. Really bad ice storms. Over in Georgia, where my family's farm is, we built a little 2-bedroom bungalow over there, and it's in a field set back from 4 big old pecan trees. Well, that ice storm, wreaked havoc on those old pecan trees. There were limbs, big limbs, little limbs, all sorts of limbs down, and we spent most of a week, just clearing out all that wood, hauling it down into the edge of the woods and just throwing it down there. But we had a lot of little stuff left over that wasn't worth carrying. We piled that on the big piles, and then we were later going to burn it. So we were over there going to burn it, called the fire people. It was a safe time to burn. They said, yeah, go for it. So we went out and started burning this pile of brush. And then, it was almost a perfectly still day, ideal for burning. It had rained recently. But all of a sudden, the wind picked up and started blowing exactly the opposite direction from the little breeze we had earlier. So we had started the fire, so the fire would be into the wind, so that it would burn into the brush pile like this. Well, the wind changed, and suddenly it was blowing the fire out into the pasture. And we started having trouble. And I had run the hose down as far as I could run it and connected another hose to that. But when we got all those hoses together, turned off on the water up at the house, it was a trickle. Why? Because all those lengths of hose with more resistance, so the water was coming out just pitifully small. So same thing with a wire. The length of the wire, the longer the wire, the more resistance you have, because those things are bumping in, remember? They're bumping into things all along the wire, and if you have a longer wire, you have more and more and more resistance, right? Makes sense, okay? So the length of wire is another resistance factor. Another one would be the cross-sectional area, okay? The bigger the cross-sectional area, the more flow you can get, the less resistance you have. The smaller the area, the more wall you have to hit per unit. length. So it's going to be that. Have you ever gone to McDonald's in the morning and got some of their really hot coffee? You probably didn't want to drink it like this. You got one of those little bitty stirrers that has a hole in it. You can sip the coffee just to see if it's too hot to drink yet. You've done that, right? Now, what if later in the day you went to McDonald's and you ordered a milkshake? Would you take that little coffee stirrer and try to drink that milkshake? You're probably going to bust your eardrums, trying to suck the milkshake up. It just doesn't work well because that little bitty thing has a lot more resistance. For hot coffee, it's fine. But for a milkshake, nah, not good at all. Same thing here. For a milkshake, you get a big old fat straw, okay? Big as you can get as much milkshake as you can with a lot less resistance. Same thing here. The larger the cross-sectional area, the less resistance. Smaller the cross-sectional area, the greater the resistance. And there's one other, and that's temperature. The greater the temperature, the more resistance you have generally. There's some materials that don't act this way, but others, and the lower the temperature, the less resistance you have. So the greater current flow. Okay, now I want you to think about something that's going out of vogue these days, but you've all still seen them. Your good old incandescent light bulb. Okay? Number one, how does that light bulb produce light? The old incandescent, not the fluorescent, but the old incandescent light bulb. Okay, you heat up a filament very hot until it glows, and that's what gives off the light. Who was responsible for that? Thomas Edison, of course. And it took him, it seems like hundreds of trials before he ever had success at it. He tried all different kinds of materials. He tried all sorts of things. Of course, one problem he had, when you heat it up that hot, it's usually going to oxidize away and burn out. So he started filling the light bulbs. You know what there's in those light bulbs? Argon. Say again? Argon gas. It is an inert gas. It doesn't react to anything, so that filament can heat up as hot as it wants, and it's not going to burn, so to speak. Okay? So the type of, so he couldn't use copper wire in that because copper conducts electricity so easily it wouldn't get hot enough to glow. Okay? So what material did he use? Does anyone know? I think we mentioned it last time. Those filaments, at least originally, I don't know if they still are, made out of tungsten. Tungsten is one of those metals. If you look at your periodic table, you'll find it in the little books in Chapter 8. In the big book, it's at the end of the chapter. Tungsten has an unusual symbol, by the way. I've got to find it here. Why can't I see it? Part of the reason I can't. There it is. Number 74. Its symbol is W. Of course, tungsten W. That makes sense. I don't know why. Okay. But it's tungsten. It's underneath chromium and molybdenum. Those aren't really good conductors either. Tungsten is not a good conductor. Therefore, when current flows through it, it meets a lot of resistance, high resistance, and therefore it gets hot enough to glow. Now, something you may have noticed about that filament. You probably can't look at it and say, oh, that's tungsten. But I bet you most of the time, if you've ever noticed those filaments, what did you notice about them? Describe it for me. There's filaments inside the light bulb. Yeah, what were you saying? Yes, a little coil. And why did they do that? So they can have a long length, but inside the light bulb, so they go like this. And if you stretch that thing out, it'd probably be something like that. Okay? So there's where the long length also gives you more resistance. The type of material, tungsten, much more resistant than, say, copper or aluminum or something like that, but also a long length. How do they get it in a light bulb? They make it in the little bitty coils, and then they run them between like 3 pegs there, so you have a lot poles there. Yeah, exactly. Now, what else do you notice about them? That filament is just about as fine as hair. I don't have much to show you, but if I did, you could imagine it. Okay, it's really, really small cross-sectional area, which increases the resistance even more. Okay, so that's why they designed the tungsten filaments like that. Tungsten, because the type of material is a poor conductor, or not a great conductor. Length, they make it into a coil so it has a lot of length to go through and very, very small cross-sectional area. So it's going to have a lot of resistance. Now, here's a dumb question for you. When, in your lifetime, I assume some of you have seen lights blow out, right? When do they usually blow out? What is the most frequent time that they blow out? When you first turn them on, okay? When you first turn them on, what would you guess would be the temperature of that filament? Sort of cool, room temperature about, right? But of course, once they're on, they heat up pretty quickly. But because when they're cool, they have less resistance, so more current flows through there. The more current, more likely to blow the filament. Okay? So that's why they usually blow out when you first turn them on, because they're cooler there. After they heat up, they have more resistance, so less current flows through there. Okay? So you see, your good old light bulb shows all four of those resistance factors. Now, I don't want to say more, but an awful lot of Nobel Prizes in physics have gone to scientists who have studied this next thing, superconductors. What a superconductor is something that has negligible resistance, but this only occurs at very, very, very low temperatures. Okay? In fact, the resistance seems to go to zero. That's why they're called superconductors. Now, it's so bizarre that just a little bit of a voltage can start the current flowing, and you can actually take the voltage source away, and the current just keeps flowing because there's nothing to stop it. It's sort of bizarre, okay? You don't think it would happen, okay? But it does. Somebody else coming in? Good. Oh, goodness gracious. This guy has shown up, huh? What do you call him, seat fried? No, never mind. Okay. All right. Good to see you. So superconductors have very low resistance. Now, here's the strangest thing. The materials that are your best superconductors, in fact, they're only superconductors, generally at normal temperatures are very lousy conductors, okay? But it's when they get very cold, something happens to their electronic structure, suddenly they conduct almost infinitely well. Now, this would be potentially a good paper topic. And by the way, folks, you realize you have technically two more weekends to work on your paper. The last day of class for this course is Tuesday, a week from next Tuesday. That's during finals week for full-term courses, but because this is a mini-term, we have class that Tuesday and then the final on Thursday. Okay? Now, I was telling the rest of the class, those that were here earlier, this, just a quick review on where I'm picturing things to go. We're having this portion of the class on electricity. My guess we'll finish electricity and go to magnetism today. And then when we do the lab at 5:45, it'll be on Ohm's law, which we had on the last slide. Okay? Now, then on Tuesday of next week, I think we'll probably finish up the electricity chapter, electricity and magnetism, chapter 6. So we'll have the last lab on magnetism, electricity and magnetism that day, on Tuesday. Then on Thursday, we will In fact, on Tuesday, we'll probably start Chapter 8, the chemistry part. On Thursday, we'll continue Chapter 8. Then we'll have a lab on Chapter, well, let's see. We may not have the lab on Chapter 8 because, well, it depends on how far we get in the chapter. If we get far enough for the lab, we'll do the lab on Thursday, okay, of next week. Okay? And then the last 30 minutes, we'll have the test on Chapter 6. So next Thursday, more than likely, we'll have the test on Chapter 6, the chapter we're on now. Okay? Now that Thursday will be our last lab. The next Tuesday, we have class, and in that class, we'll finish as far as we can get. I think we'll finish Chapter 8 in that class. Okay? Now, if we finish, and we don't have a lab, if you want to, this will be up to you, you can either go home, that'll be fine if you want to go home, and then come back Thursday, which is our final exam day, and have the test on Chapter 8, and then the final exam. Both of them are fairly short. You'll have 4.5 hours to do both of them. Okay, so it's not going to take you an hour. Probably not 45 minutes to do it. But anyway, but that's technically the next Thursday. If you don't want to take both tests on that Thursday, and you want to take your Chapter 8 test on the previous Tuesday, that's not next Tuesday, but the following Tuesday, you can do that. I'll let you do that if you want to. That way, when we finish the lecture on the chapter, if you want to take time to do your formula and equation sheet, whatever, I'll be here until 7:45. You can take your test anytime you're ready. Or not. You can wait till Thursday to take it. Now, not only that, but if some of you want to take the final on Tuesday, if you have time, I'll let you do that as well. I'll be here Thursday. That's technically when the final is. But if some of you are wanting to get over, get through, and get out, rather than wait around till the last possible minute that Thursday evening, I will be here so you can do it either Tuesday or Thursday. That's the finals week, not this week. So just wanted to let you know since a few people would come in. Okay, so that's what superconductors. Now, the very earliest superconductors, they had to get it down there almost, and when we're talking low temperature, we're not talking 25 degrees Fahrenheit. No, we're talking about 2 degrees, 2 Kelvin, almost to absolute zero, okay? Now, that's really cold, okay? And you would think superconductors, you can do a lot of great things, and you can, but you've got to put in so much energy keeping them that cold before they become superconductors, so it doesn't really gain you a lot. But, now this, yes?
Those temperatures aren't, they have to be produced that way?
Yeah, oh goodness.
They're not on
You have to do some pretty major production to get them down there. I mean, you're talking about, okay, some of you may have dealt with dry ice, have you? That's solid carbon dioxide. I don't know exactly what temperature that's at. I'm guessing probably minus 20 or minus 30 Celsius, okay? Which would be still over 200 K, okay? It's not very cold, okay, in the big scheme of things. Cold to us, but not very cold. We're talking about, some of you may have dealt with liquid nitrogen, have you? That's pretty cold stuff, okay? Now you're getting down into probably 35 to 50 K. The early superconductors were way colder than that. You're down in the liquid hydrogen and helium range. Really, really cold, okay? Now, like I said, several people have won Nobel Prizes for this because different groups have come up with superconductors that superconduct at higher temperatures. And once they can get them up into the liquid nitrogen range, we can deal with that because that's a fairly common thing. It still takes a lot of energy to produce it, but that's what. I don't know this for sure, but I'm just going by old memory on it. In Japan, I'm pretty sure it is, they have some type of super fast train, a bullet train, And they have a name for it, I just can't remember it. And if my memory's right, one reason it can go so fast is that they have a very, very cold spacing below the track that's cold enough to have a superconductor running a current, pretty good current, and anytime you have a movement of charge, you produce a magnetic field. And that produces such a strong magnetic field that literally the train is elevated off the track and is never touching the track. And that's why there's basically no frictional resistance there. You have some air resistance, but no metal-to-metal resistance at all. It elevates that train and they fly, okay, because it's cut down the resistance. That would be a good paper topic. That's what started this whole thing about the end of the term. I was thinking, please get your papers in. You only have 2 weekends left, this weekend and next weekend, to work on it. You get it to me. I can't remember how I said that. I believe you got it to me in October. Did you get 3 bonus points? November, 2 bonus points. And the first week in December, 1 bonus point. But so next week, now we're in December, you get it to me today, tomorrow, or next week, you still get a bonus point. But you get it to me finals week, no bonus points. So in other words, Tuesday will be no bonus points. Not next Tuesday, the following Tuesday. All right, so that's more on resistance. Any questions about resistance? All right, now we're moving to, before we do that, let's do example 6.3. Let me back up. Goodness, I need to find a place I can do it. 6.3. A light bulb in a 120 volt circuit. Now tell me 2 things. First, what's a 120 volt measuring? Voltage. Very good. Pretty easy question, right? What kind of circuit do you think that's on? 120 volts. Multiple choice, AC or DC? AC for sure. DC at 120 volts, that's one big powerful battery you got. You're going to be shocked and burned up. I mean, it's going to be really hot. 120 volt DC is almost unheard of. 120, that's almost always AC. Okay? Is switched on and a current of 0.50 amperes. What's the symbol for that? Oh, this is V. You told me. I. Current is the symbol, the parameter for it is I. Okay? It flows through a filament. What is the resistance of the bulb? So what we're looking for is resistance. What would be the resistance of that bulb? Ohm's law. What would that tell you? V divided by I. And V, we said, was 120 volts divided by 0.50 amps. And that would be what? Anyone got a calculator? Can you do it in your head? It's really easy to do it in your head. Or on paper. Move this decimal one place that way, which means move that one place that way. 240 ohms. Very good. Okay. 240 ohm. Okay, never mind. We're not going to that. Okay. 6.4 says, what current would flow through an electrical device? So now we're looking for what current. That would be, what's your unknown here? What current? I. That's your unknown. That's what you're looking for. Okay. What current would flow through an electrical device in a circuit with a potential difference of 120 volts? What's that a measure of? Voltage. Okay. Potential difference. Electromotive force, EMF, whatever you want to call it. Okay. And a resistance of 30 ohms. Okay. How would you find I? Second, Ohm's law again. How would that go? Second? V divided by R. You got it. And your voltage was? 120 volts, and your resistance was 30 ohms, and that would be 4 amps. In fact, probably 4.0 amps. Okay? No, they just say 4 amps. It doesn't matter. Sometimes they use significant digits, sometimes they don't. We can't say for sure if that's it. Now, let me just give you a few rules of thumb here. A current of 0.5 amps is a pretty good sized current. A lot of our currents that we deal with are milliamps, thousands of amps. So 0.5 is not a huge current, but it's not trivial. 4 amps, that's quite a lot of current. You're going to have, and by the way, when you have a lot of current, you usually have a lot of heat produced. So that's going to be pretty, and the reason is 30 ohms is pretty low resistance. 240 ohms, that's relatively reasonable resistance, okay? So anyway, you see how Ohm's law works. All right, now we're ready for electrical power and work, okay? Tell me, what's the unit for electrical power? Someone's mentioned it today already, but it was in a different one. Watt, yeah. What's the unit? Watt, yeah, okay. Okay, work. What do we use to measure work? Force is a force. Force is a vector quantity. Work is a scalar quantity. They're related, but not the same. Work is measured in same unit as energy. Huh? Energy. A couple of labs ago, we had the pendulum. What was the energy? Kinetic energy, potential energy, huh? What was it measured in? Joules, exactly, okay? So electrical power measured in work and watts compared with work, which is measured in joules. How are work and power related? Third cousins, twice removed. No. How are they related? Is there any relation between work and power? This is several labs ago when you ran the stairs. Remember that one? How are they related? Yes. Me and the, oh goodness, what do you call these things? Bobcat. That illustration we did. Say again? Force is a force, okay? That would be measured in newtons. Work is force times the distance. That's measured in joules. What is watt? Me and the Bobcat. We did the same amount of work. What was the difference? It took me several weeks. Time was the difference. So time's the factor. How is work and power related to time? Power is the time rate of change of doing work or expending energies. That's what power is. So in other words, work is power times time. That's what we're going to get at down here. 3 circuit elements contribute to work. Your voltage source, this was in the last lab, you ran into these. Voltage source, which you sometimes call your battery, sometimes your, what do we call it? Voltage supply, that kind of thing. Your electrical device we called the load. That was our light bulb in the last lab, right? That was the load. And then we had the conducting wires. Okay? Conducting wires. The pathway. You have to have all 3 of these to have your circuit elements to work. Okay? Now, these 3 things, the conducting wire, maintain a potential difference across the device. The input wire is at the higher potential than the output wire, which is going back to the battery. Okay? Now this is in conventional current. We had that illustration earlier today too. I pointed you back to it. The input wire is at higher potential than the output wire. Okay, which just says that. The output wire is sometimes called the ground on AC circuits. Now, I notice you guys, especially I think the automotive folks, you must use ground a lot. Maybe the electronic people too. Most of the time with DC, we refer to it the low potential. Okay, the ground is okay, but ground is mostly used for AC because guess what? There's no current flow. It just goes back and forth. You just have to have ground at the end. Okay. Now, if there is no potential difference, then you have no current. Okay, go back to Ohm's law. If there's no potential difference, there's no current. And here's the illustration of that. How many times have you seen birds up on the power lines? Why aren't they fried? Because there's big amounts of electrical energy going through those wires. Huge amounts. And guess what? They don't have a lot of insulation on them either. So that's not the reason. The reason is the birds aren't grounded. There's no pathway for that electrical energy to go through them. If you were to, I don't recommend this, but if you were to take a metal rod and hold up there to the bird, and that's connected to ground, you'll have fried bird, okay? I mean, just like this, okay? But if there's no connection to ground, they're not going to. They can sit on the wire all day long. They don't even know there's electrical energy flowing through it. It doesn't bother them at all, okay? Now, along with that, this is sort of a bizarre little story. Our first dog was a pretty smart dog, okay? She kept us going. She was a lab golden mix, and they were retrievers, and she was a sweet dog, really, but she was a pretty sharp dog. And we had a dog right next door to us, and when she was a little puppy, I made a bad error here. I made it so she could get under the gate, under the fence, to go to the neighbor's yard so she wouldn't be lonely. She loved Allie, who was a German Shepherd that lived next door. And so we'd let her in the backyard. She might take care of business. Then immediately she'd be under that fence to go see Allie. They played and stuff like this. And they had a big time. Okay? Well, later, she became a big dog. When she was a puppy, I thought that was fine. When she got bigger, I thought, okay, I only made a little hole there. And when she got bigger, I plugged the hole. Didn't stop her. She managed to get out. And we, for a long time, couldn't figure out how she was doing this. And finally, we caught her in the act. Big dog, 60 to 80 pounds, and she could get under a chain link fence that looked like it was into the ground. She would push and force and bend that thing until she'd get flat on the ground. Almost like a cartoon. I don't know how she got under that, but she did. And I would take stakes and drive them in with horseshoe nails, what do you call those? Staples, driven into the stake, holding that thing down. She'd managed to get out. And finally, a neighbor told us, a different neighbor, he said, only way you're going to stop her is with electric fence. Only way that's going to work. It's not going to hurt it. It'll tingle, but it's not going to do any major damage. You'll never stop her until you do that. He had dogs. So we thought about it, tried different things. Oh, I put barbed wire down there. Okay, thinking she's not going to do that. She went through that. Nothing was going to stop her. So we finally agreed with what Woody said and put electric fence there. Low voltage, low thing. Yeah. And she was a stubborn cuss. And he said, and here's what Woody said. He said, she gets out once, no more than twice, she'll never even get near it again. You can turn it off and you won't need to be wasting any energy. Not Casey. We finally watched her and we swore this must be what she was doing. she'd go up to that fence and get real close to it, and we think she let her whisker touch the thing, and if she got a little bit of a vibration, she'd back off. Now, she had a better way to do that when she could do it. If I was in the backyard, we had a garden area too back there, and we had to keep her out of that too, so we had to put electric fence around that. We found that she loved cantaloupes. When they were about this size, she'd pull them off and play with them like balls. So we had to keep her out of the garden too. Then when we put that down there, she started jumping over that fence because it wasn't as high. So there was just no keeping her out if she wanted to go. But when I was back there working in the yard or in the garden, what she would do would come up by me and just be such the sweetest little dog and rub against me and stuff like that and keep pushing until she pushed me into the wire. And when I jumped back, she knew the power was on. I wanted to strangle her, but she would do that. And I'm ashamed to admit it, she did it more than once. I mean, any chance she'd get, my wife, I could hear her scream, because she'd just be so sweet and just get and push. And if we jumped, then she knew the power was on. So we never could turn it off. Well, we went back there one day. I came home from work and went back to let her out, see how she was doing. And there was a squirrel. It was like this. It had gone up and reached to touch the wire and then electrocuted itself. So it wasn't enough to hurt her, but the squirrel didn't fare too well. Of course, I wasn't too sad about the squirrel. Okay. The squirrel could run along the power lines out there and not bother it at all. But if it was grounded and touched that, very low voltage got out. Okay. Actually, what happens is that current freezes your muscle, and then it held it that long. Long enough. Okay. So what is power in circuits? Power is current times voltage. Who would have ever thought that? Okay. Current times voltage. Well, remind me of what current is. What unit is it? Huh? Current. Say again? Current. Amperage. Okay, and what is an amp? The other Frenchman? Say again? Ampere, right, but what is an amp? What is the definition for current? Charge per unit time, which would be coulombs per second. That's what amp is. And what's voltage? I've mentioned that at least once or twice today. Voltage is energy per charge. Energy would be in joules, and charge would be in coulombs. Well, looky here. The coulombs go out, and what's our unit? Joules per second, which is a joules per second is a what? You've already named it today. Time rate of change of using energy. Anyone make a guess? Power, very good. How did you know that? Okay. And power is measured in what unit? Watts, exactly. A joule per second is a watt. Goodness, I feel like a dentist here. That's what power is. It's current, which is coulombs per second. Time rate of change in the charge, movement of the charge per second, times voltage, which is joules per coulomb, energy per unit charge. Coulombs cancel out, you get joules per second, which is what a watt is. Now, once a month, if you're head of a household or do anything with a household, you're going to get a bill from a certain company in town, not in this town, in the state, okay, dealing with electricity. What do you call that? Your power bill. Does that mean you're paying for the power you use? No. What are you paying for? Not kilowatts, that's power. If you'll notice on that bill, what are the numbers that you're paying for? The units for it. It has kilowatt in it, but it's not just kilowatt. Kilowatt hours. Kilowatt hours. If you have a watt or a kilowatt and then multiply by time, that gives you energy. Okay? Multiply this by time, that gives you joules of energy. Except the joule is a very small amount of energy. A kilowatt hour is a lot of energy. Okay? Because a watt is a joule per second. A kilowatt would be 1,000 joules per second. Multiply that by 3,600 seconds in an hour. That's a lot of joules. Okay? And that's what you're paid for. Kilowatt hours. So your electric bills, you're not buying power, you're buying energy. So the cost is the number of watts times the number of hours. That would be watt hours times your rate. And of course, the 1,000 down here changes watt hours to kilowatt, watts to kilowatt. That gives you kilowatt hours times the rate. Dollars per kilowatt hour. By the way, our electricity is relatively cheap. I don't know what the rate is right now. Last time I checked, it seemed like it was like 17 cents per hour. 17 cents per kilowatt hour. It may be more or less than that. I don't know. But it was somewhere in that range. But less than 20 cents, usually, per kilowatt hour. And kilowatt hour is a lot of energy. So we are really spoiled by cheap energy. Really. Okay. But anyway, you're buying and paying for energy. The cost is not watts. You're not paying for watts or kilowatts. You're paying for kilowatt hours. And that's what you do. I think that is going to lead to, let's see. Oh, and in the old way of doing, when we used to use E instead of V, I liked it better. It said P is equal to IE. I love pi, so I always remember that one. And guess what? You can do the same trick on the circle or the triangle. What were two other ways to express that one? Okay, we're going to get there in a minute. Just using those three letters without any powers. I is equal to P over E, and E would be P over I. Got it. Okay. Now then we can start substituting what E is, or what V is, I'm sorry. This could be V, E or V. That could be E or V. Okay, then we can start substituting what V is, IR from Ohm's law, and you can get all sorts of other combinations. And we'll do that in a minute. Okay, let's go, I think, now to, before we get to magnetism, let's back up here. Let's see, we can do it here. I'll just erase all the ink from the slide. Okay, let's do example 6.5. A 1,100 watt hair dryer. 1,100 watts. What is that measuring? Power, that's your P. Okay, very good. Is designed to operate on a 120 volt circuit. What is that a measure of? Voltage, okay? How much current does the dryer require? So current is measured at, what's the symbol for current? I. That's what we're looking for, how much current, and what's the relationship between current, power, and voltage? Current? Yeah. You gave it to me just a minute ago. I just erased it. P divided by V, exactly. And your P is? Say again? No, right here it gives it 1,100 watts divided by 120 volts. What did you say? 9.6. What unit? 9.16. What unit? Amps. Very good. And that, by the way, is a lot of amps, but that makes sense because this was a hair dryer. Hair dryers produce a lot of heat. Anytime you've got devices producing a lot of heat, the odds are it's using a lot of current. Okay? Because those two usually go together. It's the current flowing through the wires that heat up, that make the heat. Okay? Now, example 6.6. An electric fan, and by the way, they round it in the book to 9.2 amps. And the reason for that is you only have 2 significant digits there, 2 there, so you need only 2 there. Okay. Example 6.6. An electric fan is designed to draw 0.5 amps. What's that a measure of? What symbol? I. Very good. Okay. On a 120 volt circuit. What's that a measure of? That's your voltage. Okay. What would be the power rating of that fan? So we're looking for P. That's your unknown here. How do we get P out of I and V? Who? Okay, wait. You're given current and voltage, and we're looking for power. Second? No. That gives you resistance. It's what? V times R, I times V. It doesn't matter which way you say it. And that would be, in this case, 60. 60 watts. Watt. Very good. Okay, you got it. 60 watts. That's about like a light bulb, by the way. So your electric fan and your light bulbs draw about the same. That's that? Okay. Now, there's a few little illustrations on your book, in your book, that you might find useful. Here we see a 100-watt bulb. That's going to be more than that electric fan. Okay? Watt, though, is power. Power times time, that would be your energy. So here is a finishing sander, and it's hard for me to read with my old eyes what that is. I can see voltage 120. That means it's AC, generally. It gives its hertz or its frequency. Amps 1.6 or 8, I can't tell. From that, you could calculate its power. You know the voltage, you know its current, you can calculate the voltage. Okay? Here's another Black & Decker. They must have shares in the business. This is a 120 volt. That makes sense. I believe that's 8 amps. And this is, by the way, a shredder, garden shredder. And let's see. You can calculate the watts from there. Now, we already mentioned them today, didn't we? The guy who's featured on page 153, People Behind the Science, good old Benjamin Franklin. Is this what he's most known for? Huh? The flying the kite? Okay. We know him for that, but if you ask just any old person what Benjamin Franklin, they say he's one of the founding fathers. Okay? He was one of the 5 people on the committee to write the Declaration of Independence. Okay? Thomas Jefferson did most of the writing, but he was on that committee. He was also on the committee, one of the few people that was on the committee both to write the Declaration of Independence and the Constitution. Now, I think Governor Morris did most of that writing, but Benjamin Franklin was there too.
He's also on some currency too.
It's what?
He's also on some currency.
Oh, yes, he's on the, I don't get to see him very frequently, but I think he's on the, was it $20 bill? Or is that Andrew Jackson? 50, that's it. Yeah, it's one of those. I don't see those bills often enough to know. Yeah. Okay. And he was also the first Postmaster General of the U.S. He wrote a thing called Poor Richard's Almanac. Okay. He had a lot of really famous sayings, little proverb type things. Penny saved is a penny earned, those kinds of things. He was quite a statesman. Not probably much of a politician, but he was an inventor. The wood stove we often call the Franklin stove, potbelly stove. He came up with that because before most of the heat just went right up the chimney from a fireplace. So he did the potbelly stove so that the heat radiated throughout the room. So quite a character. And in my guess, in my mind, I bet you he interacted quite a bit with Coulomb and Ampere. If they lived at the same time, which I think they sort of did, because he lived to a ripe old age of 84. Huh? Ripe old age of 84 years old. That was pretty old for those days. What's that? He's on the $100 bill. Yeah. I don't see him often enough to know. Okay. So they have another little table here before we leave electricity. The summary of electrical quantities in units. Charge, the basic unit for charge is the Coulomb, which is the number of electrons times the basic fundamental charge of electron. Okay? Electric potential is voltage, and that's energy or work per unit charge, joule per coulomb. A volt is a joule per coulomb. Really handy table here. If I were doing a formula equation sheet, I'd be sure to get this on it. Current is charge per unit time, and that's Q per T, which is coulombs per second, and amp is a coulomb per second. Electrical resistance is voltage per unit current, so that's ohm is a volt per amp. And electrical power, P is equal to IV, which is measured in watts, and that's a joule per second. Okay? And you cancel the other units out. Now, there's an interesting little concept applied here, shocking cost. Okay? You can predict the cost of running an electric appliance just with a few calculations, and we've done some of those, and you can see them. Find the answer to one or more of the following questions about the cost of running an electrical appliance. What is your monthly electrical cost for watching television? I bet you it would be more than you guess, okay? See if you can look that up and see. Actually, it's gotten a lot cheaper lately. In the old days, what's in the back of those television sets? Vacuum tubes, exactly. If you ever felt back there, they were always hot. And when you have heat, you're losing energy. When they went to transistors, you got huge energy savings. But of course, shortly after, or about the time of transistors, they went to color TV, which probably produced more heat than black and white TV did. So you got some loss there. Now the plasma screens, they're probably a little more efficient. But in the flat screen, there's not much there, but they don't get hot. If you felt back there, they don't. So actually probably not as much as you used to cost. Okay? How much what is the cost of drying your hair with a blow dryer? More than watching TV by a long shot, because there's a lot more heat produced. Anytime there's a lot of heat, that's money going out the window. Okay? How much would you save by hanging out your clothes to dry rather than using an electric dryer? Big time. And no one does it anymore. I like to use those solar clothes dryers. Hang them on the line. I love it. My wife doesn't. We don't have one. Okay. Compare the cost of using the following appliances. Okay, you give me a guess. Your cost. Coffee maker, toaster, can opener, vegetable steamer, microwave oven, blender. Which of those do you think would be the most expensive or the least expensive? The toaster is probably close to the most. Coffee maker may be close because that uses heat too. What would be and vegetable steamer would probably be pretty expensive. That uses heat. Which would be the cheaper ones? The can opener and the blender would probably be pretty cheap. Okay? The microwave oven, much less than anything that produces heat. Because if you ever felt a microwave oven, it doesn't get hot. The food gets hot, but the oven doesn't. It saves you big time. Okay? So it's usually at one of the cheaper ones too. So about like a light bulb, sometimes. The old ones were anyway. Okay. How much does the electricity cost per month for the use of a desk lamp? Minuscule. Not very much at all. Cents, no dollars. Okay. Very cheap. Of the electrical devices in a typical household, which three have the greatest monthly electrical cost, would you say? Say again? Think heat. Your stove, especially if it's an electric stove, big time. Okay? Another one? If you don't use the clothesline? The dryer, big time. Big expense. Yeah, possibly. It depends on how much you cook and how much you wash, okay? And probably the next one would be your, especially if you have electric heat strips, those are going to be really expensive. But even the cooling system, that heat you don't see, but it's being blown to the outside. Yeah, go out there and feel that thing when it's running. Yeah, it's hot. Pours that heat out. So yeah, those are your big expenses probably. Okay. Let's do example 6.7. Okay. What is the cost of operating a 100-watt light bulb? What's that a measure of? Power, exactly. A 100-watt light bulb for 1 hour. That's your time. Okay. If the utility rate is 10 cents per kilowatt hour. Yeah, it's going to be pretty close to that. What you do is multiply your 100 watts times 1.00 hours, and that gives you 100 watt hours, right? Okay, watts times hours is watt hours. Well, write that in kilowatt hours. You'd move your decimal 3 places, and that would be 1/10 of a kilowatt hour. Multiply that by 0.10 kilowatt hours. Notice how the units go out, and that gives you not 1/10 of a cent, no. Yeah, that would give 1 cent. 0.01 cent. That would be how much it is. 1 penny to run the 100-watt bulb 1 hour. So let's do example 6.8. An electric fan draws 0.5 amps. What's that a measure of? Current. What symbol is that? I. Okay. In a 120 volt circuit. What's that a measure of? Voltage. Okay, very good. Okay, you got it. What is the cost? So again, we're looking for cost of operating the fan if the rate is 10 cents per kilowatt hour. Okay? And y'all were getting us off to a good start. You said current times voltage gives you power. So that would be P is equal to What would that be? I times, which is I times V. Okay, 120 times 0.5, and that would be 60 watt. Watt, very good. Okay. Now that 60 watts is, and does it say, it says, okay, what is the cost of operating that? And it doesn't tell you a time, so this is going to give you, if you multiply that 60 watts, well, let's change it to kilowatts, what would that be? You have to move your decimal 3 places to the left, and that gives you 0.06 kilowatts. Okay? Okay, yeah, well, we'll see. Let's start. Times 0.060 kilowatts. Now, what you can do here, cancel out the kilowatts, but leave the hour, and this gives you 0.006, or 0.6 of a penny per hour. So to run that electric fan, it's going to cost you 0.6 of a cent per hour. So you can run it all day long and not really spend a lot of money. Okay? Good deal. All right, any more questions on the electricity part? Okay? Now let's move to magnetism. I saw some folks leaving, or y'all know if they're gone for good. Someone left a computer, so I guess someone's coming back. Yeah, I guess Michael's coming back. I don't know about Heidi. Okay, how are we doing on time? 5:06. 5:06? Okay. Yeah, well, we've been going since 3:15, so we haven't been going quite 2 hours, but let's take a 5-minute break. We'll come back and we'll wrap up. So I'm going to put this on pause, or put my pause. All right. We've done at least part of the electricity part. Now we move to the other half, which is magnetism. It's not quite half the chapter, but it's a fair. Now, people have known about magnetism probably almost since recorded history began, okay? We've used magnets for what? What's that? Yeah, the world's a magnet, and we use that fact how? How? Huh? Sorry. Well, okay. It does the same thing. It helps us find their way. Compasses. The old compass was how sailors and soldiers and anyone, the explorers, that's how they sort of had an idea where they were. The earliest ideas, we knew that that certain types of rock, okay, were naturally occurring magnetic, okay? This type of rock had a common name of lodestone. The mineral name is magnetite. Magnetite. Now there is another mineral whose chemical composition is identical to magnetite, and it's called hematite. The thing is, hematite is not magnetic, but magnetite is. And there's a reason for that. We'll get into that a little bit later. Okay? But that was the first known magnets that came out of this naturally occurring magnets called lodestone, which now we know to be the mineral magnetite. Now, what people used them for was to make magnets out of certain types of materials, and then they used those magnets to help them as a compass, to guide them where they were headed. Magnetism is characterized by poles. Now, if you think back on charges, electricity was characterized by charges. You had positive charges, you had negative charges, okay? And on those charges, like charges repelled each other, and unlike charges attract each other, okay? Well, magnetism is similar to that, only it's characterized by poles. You have the north-seeking pole and the south-seeking pole. If you have a north-seeking pole here, say swinging freely here, it's going to point basically north, okay? So it's going to point a little like this, but we'll get into that later, okay? If you bring another north-seeking pole near it, it's going to repel that one away, and it won't point north anymore. However, you pull a south-seeking pole toward it, it's going to be attracted to that. So these are the north-seeking and the south-seeking poles. Okay, this is sort of strange. Besides lodestone, there are other magnetic materials, and basically only 3 elements are magnetic. Okay? These 3 are iron, nickel, and cobalt. Again, if you go to your periodic table, in the very back inside cover of your book, now if you find iron, it, by the way, is Fe. Now I know why that was called Fe, because it's either Greek or Latin name was ferrous, which really meant fire. You got iron by, refined iron by heating up iron ore and melting away the dross and lead of that. But then you look right to the right of iron and you have cobalt. You look right to the right of cobalt and you've got nickel. Those 3 elements are the only 3 naturally occurring magnetic materials ever. Okay? Nothing else on either side or below or anywhere else is magnetic. Only those 3. Okay? And we call these the ferromagnetic materials. Ferro from iron and other magnetic materials, cobalt and nickel. Now, if Nick were still here, he took my Physical Science 111 course earlier, a couple terms ago, and he would have been able to tell you that the Earth is made mostly of iron. Okay, it's not on the surface, but deep, deep inside is mostly iron, as is most of the stuff in our solar system. The solid material deep, deep inside is usually iron. Okay? Next most frequent of those deep, deep inside is nickel. Not much nickel on the surface, but deep, deep, there's plenty of nickel. Just not economically feasible to mine it. Cobalt, I don't think is that much. Okay? But there is some. Of course, it's out there too. Okay? So those are your 3 naturally occurring magnetic materials. That's the earliest ideas, that's what we knew about it. More recently, we have a better understanding. Magnetism is associated with magnetic fields, just like electricity is associated with electric fields. It all starts in the field, okay? And just like we have electric field lines, we also have magnetic field lines. So you have to have some convention to talk about these. What was our convention for electric field lines? They pointed away from positive charges. They pointed toward negative charges. Well, we need some sort of convention for our poles, too, the field lines between the poles. Here's the convention. They point away from north-seeking poles and toward south-seeking poles. That's your convention there. Okay? Now, the magnetic poles and the fields, like I was just describing, they are inseparable. Just like charges and fields are inseparable of electricity, magnetic poles and magnetic fields are inseparable. And if you have a magnetic pole, you got fields around it. You have fields out there, somewhere there's a pole. There's got to be. And here's the difference, though, between electricity and magnetism. You can have an isolated positive charge, no sweat. You can have an isolated negative charge, no sweat. Can you have an isolated north pole of a magnet? No, you can't. They always come in north-south pairs. And let's see if this next, okay. If you could do this, this would be a little experiment to try. Okay, now in the book, they don't show it here, but in the book, on page 155, there's a picture of a pretty strong-looking bar magnet. You can see the North Pole, you can see the South Pole. And what that fuzzy stuff is iron filings. That's a pretty strong magnet. They dip that magnet into iron filings. And we're going to do this in the next lab, by the way. Not dipping a thing, but we're going to use iron filings. And you see around the North and South Poles the iron filings are greatly bunched together, right? Whereas in the middle, there's hardly any. Okay? So it looks like to me from that most of the magnetism resides in the North Pole and near the South Pole. And that's absolutely true. So therefore, let me try this. There's not much magnetism in the middle of that bar magnet, right? So let me cut that in two. If I could, I'd break it in two. However, get it into two pieces. Have you isolated a North Pole and isolated a South Pole now? No, you haven't. Because right where there's no magnetism at all, as soon as you break it, that becomes a South Pole, that becomes a North Pole. Immediately, they always occur in north-south pairs. Okay? If you broke those again, you'd have a south here and a north there, a south here and a north there, a south here and a north there. Everywhere you break it, you're going to have another new pole. Okay? That's why on those refrigerator magnets, you've seen those little bitty discs, right? You can take a magnet that's this long and cut it into as many pieces you want, north, south, north, south, north, south. That was one magnet to begin with. You can raise as many magnets as you can cut. Okay? So the poles always come in north-south pairs. Field lines go from the north to the south. That's what we were talking about before. If you were to draw the field lines here, you have arrows pointing away from the North Pole and toward the South Pole. In fact, the next slide, I think, is going to show that. Let's see if it does. Yeah, here we go. The field lines emanate from the North Pole of the magnet and go toward the South Pole of the magnet. Okay? Now, where is the magnet the strongest? Where the field lines are the densest. At the North Pole and at the South Pole. That's why you have that aggregation of the iron filings there. Okay? Now, like magnetic poles, I already mentioned this one, repel each other. Unlike poles attract each other. A north and a north repel. A south and a south repel. A north and a south attract. A south and a north attract. Okay? Now, how do you tell? You don't see these field lines. How do you tell where the field lines are? You get you a little magnetic compass and put it somewhere close to the magnet. The point of that compass is going to point away from the North Pole toward the South Pole. If you put it up here, this end would be pointing away from the north. That would be pointing ultimately toward the south. If you put it down here, the point would be toward the south, the other end the opposite direction. Okay? Wherever you go, wherever it is, it lines up in points like that. And that's how you define those field lines. Make sense? Okay. Now, I don't see any slide here. I'm not sure if there's supposed to be. I think the one with the globe is going to show up later. If not, we'll come back to it. Okay? Now, where do these magnetic fields come from? They just can't exist out of nowhere. I mean, people thought, well, they just come from lodestone. No, they have to come from somewhere. Here's what's happening. What we observe on the macroscopic scale, you can almost guarantee there's some reason down on the microscopic scale. And sure enough, there is. And I'll give you this secret. It's not a secret. I'll give you this statement, and we're going to use it over and over again. Whenever you have the movement of a charge, you have an induced magnetic field. Whenever you have a moving charge, you have an induced magnetic field. So, what we have on the submicroscopic, the atomic level, the intrinsic spins of subatomic particles, that's movement of charge, electrons, protons, and so on, they produce magnetic fields. The orbital motion of electrons around an atom, that produces a magnetic field. Well, guess what? Electrons move around every atom. So why aren't there magnetic fields everywhere? Because usually the movement is random. And if it's doing it different things, then it's not going to produce a magnetic field. So it must be, and I can't tell you any more than this, that on iron, nickel, and cobalt, the movement must be, on average, regular enough that it does produce a magnetic field. But then you might say, but not all iron is magnetic, not all cobalt is magnetic, not all nickel is magnetic. Why is only certain ones of them? Because every atom has an intrinsic magnetic pole, but some of them could be pointing this way, some that way, some this way, some that way. So again, the random pointing wipes out the magnetic fields. So now let's consider on the macroscopic level. Okay? Permanent magnets that's made out of iron, nickel, or cobalt, that's all. You can't make them out of anything else. Okay? These permanent magnets are that way because you somehow have lined up enough of those atoms to be oriented in the same direction. We'll talk about that a little bit later. How can we measure things? Because the Earth acts like a magnet. And I think Emmanuel said that earlier. Okay? Anytime you have an electric current, you are inducing. Current is a moving charge. You're inducing a magnetic field. And this leads to the concept of electromagnets. And we'll get to those a little bit later too. Okay? I thought we were going to show the Earth there. I think it's coming up later. If they don't show it later, we're going to come back and I'll try. Well, you can look at it in your book. On page 155, bottom figure 6.21, the Earth acts like a magnet itself. Okay? Now, and coming from that, we have the lines of declination, they call it, on the U.S. map. I think that's coming up later. We're going to get to that. But we're now going to the figure 624, which is on page 157. Again, the book isn't lining up the slides with the book, with the PowerPoint too well. Okay? Here is actually a piece of iron, nickel, or cobalt. But this one's not magnetic. Now notice they have little, and they call these domains. These domains you have, for every domain you got pointing this way, you have another one pointing that way. For every one you got pointing that way, you have another one pointing that way. Every one of these domains acts like a little magnet. But because they're randomly distributed here, and not just pointing north, south, east, and west, but pointing in all sorts of directions, this is not magnetic at all. Okay? Now, on those naturally occurring magnetite, what you have there is more of the domains are pointing. Some of them are still pointing opposite directions, but most of them are pointing in the same direction. That's what makes it a permanent magnet. Okay? Not just that, if you put it near a permanent magnet, where most of these are done, then it's going to line those up so it acts like a magnet. But if you remove the magnet, then they may go back to random orientation. How can you make them permanent? Put them in the presence of a strong magnetic field like these are, and then bang on it. Stroke it. Do something to it, and then you're going to line them up, and then they don't go back. Okay? And that's how you make a permanent magnet. We'll do that in lab 2 if I could just find some pins or needles that are already magnetized. I've been doing this for so many years. Just about every pin I have is magnetized now, but I'll see if I can find some before the next lab. That'll be Tuesday. Got to remember to do that this weekend. Okay, so number 1, you've got to have ferromagnetic materials. What are the 3 elements involved in ferromagnetic materials? Iron, cobalt, and nickel. Very good. They've got to be one of those materials, or a mixture of those materials. Okay? Number 2, you have to have your atomic magnetic moments, that's what these little arrows represent, the electron, proton, intrinsic moments, or the electron orbital motion. Whatever you've got to have those lined up in these little packets. These clusters of atomic moments align in domains, and that's what these are, your domains. If it's not magnetized, even if you have magnetic materials, that means the domains are randomly oriented, so they cancel each other out. But when they're magnetized, that somehow you have forced them into that, then you have this permanent magnet. They are magnetized. Now, we will make, if I can find some, let's see, did she just make it in under the bell? I think she did. It's not 5:45 yet, is it? Okay.
This close enough of that.
Just made it in. Okay. So this is what makes a permanent magnet. You have to have ferromagnetic materials, or there's no hope. You have to have these atomic magnetic moments. All the ferromagnetic materials have those, either from electron-proton intrinsic moments or electron orbital motion. Got to have a movement of charge to make a magnetic moment. These have to form in clusters, okay? They always generally do. When they're not magnetized, that means that these domains are randomly oriented. When they're magnetized, that means they're aligned, more of them in the same direction without being randomly oriented. Okay? Okay, here they're finally getting to the Earth's magnetic field. This showed up in the book before. Now we're going to deal with it. Now the slides are out of order. The Earth's magnetic field originates deep beneath the surface. Okay, now let's go back. If Nick were here, I'm sure he would be able to tell us. The Earth is made up of several components. The very thin outer crust, that's where we live, and that's where all of our mining happens, that's where everything happens, is in that very thin outer crust. Inside that, we have some pretty heavy rock that's called magma. Now, I'm not just talking about the bedrock that you dig down low enough, you're going to hit rock. That's still in the crust. But if you go really deep, deeper than any mine I know about, and way deeper than water wells and probably even the oil wells and stuff, you get into the magma. Magma is still solid rock, okay? But inside the magma, now you have molten rock. Because the thing is, if you rub your hands together like this, they just push them together and rub, and notice what you get. It gets warmer. Well, guess what? In the Earth, all that stuff on the surface is being pulled in, and the stuff inside that, and the deeper you go, the closer those molecules are forced together. They're always in motion, and that motion produces heat. So even the magma is probably a little bit warmer than the crust, but it's not warm enough to melt. But by the time you get to the outer core, that is hot enough to melt the metal. Now, most of that metal is iron, by the way. Okay? Now, we're not going to get into it now, but inside the inner core, the molten core, you run into a solid again. Now, the reason for that is the pressure is so great, it's forced the liquid back into a solid. Even though it's very, very hot, it's still, the pressure is such that it makes it a solid again. We're not worried about that. We're looking at that outer core, which is liquid. And guess what the Earth is always doing? Spinning. So here we have mostly iron, liquid iron inside, and the Earth is spinning. Of course, the solid part is going to spin. The liquid is not going to spin as much. It's going to swirl some. But guess what? You have friction there between the inner part of the magma and the outer part of the outer core, and that liquid bumping against there, you're going to be knocking off electrons. So guess what? Those electrons move as the spin moves. And when you have a moving charge, you have a magnetic field. That's why the Earth acts like a magnet, because it spins on its axis, spins like this, the charges are like this, so it gives it a magnetic moment. Okay? Now, the sad part is that the Earth's magnetic field is not, magnetic pole is not quite the same place as the true North Pole. It's close, but it's not quite the same. Okay? On this map here, north of Canada, it's in the Bering Sea, I think. I can never see there it is right there. Near some little island, really close. Here's the true North Pole. Here's the North Magnetic Pole right there. It's off just a little bit. Not much. Look at the whole globe, not off by much at all. But if you happen to be over here and your compass is pointing to the North Magnetic Pole, but the true north is here, you've got a little bit of error. Okay? What's that?
Sarah Palin said she could see Canada from her.
I thought she could see Russia, but no. She has good vision. I don't know. We won't make any more comment about that. Now, if you go down south, it actually gets a little bit worse. Okay, if I can find it here. Here is a south magnetic pole here. That's even further from the true South Pole. But I've not been in the southern hemisphere that much. I have a little bit. Your magnetic compass is probably not going to line you up too good down there, especially if you're over here in Samoan Islands and you're pointing toward the south magnetic pole. The real South Pole is here. That's pretty far. Pretty big error there. What those errors are called are errors of declination. Okay? Because the true north is not lined up with the magnetic north. So the magnetic North Pole, okay, I'm sorry. Yeah, magnetic declination is offset a little bit. And the direct, okay, now we'll get into the next part later. Let me show you what that, okay, here's that picture of the Earth. The Earth acts like a magnet itself, a permanent magnet, because it's got charges moving around. But in reality, if you think about it, if your north-seeking poles are pointing this way, if you call that the north point of your magnet, it has to be pointing to the south. So actually, that north magnetic pole is actually acting like the south pole of a bar magnet because it's attracting the north pole of another one. Like poles repel, unlike the track. So that's why they have this drawn upside down, because really that's what it acts like. Okay? Now, here is the U.S., and it shows some of these lines of declination. Okay, magnetic declination, the offset. And we are pretty lucky. Right here, it looks like it almost goes through Atlanta, maybe a little bit east of Atlanta, is the zero line of declination. In this place, the north magnetic pole is lined up right with the true north pole. We're over here in Birmingham, about where this is. I can't read that, but it looks like it's 2 degrees. Yes. Only 2 degrees off. That's close enough for government work. Okay? And up here, is that 6 there? 5 or something like that. Yeah. So we're not far off here. However, if we're up here in Washington State, that looks like about 25 degrees off. That's enough to make some pretty serious error. So magnetic compass will give you the general idea of where north is, but you're off a little bit. If you're up here in Maine, you're off by, what is that, 15 degrees? 18 degrees. So you see, depending on where you are, it's not going to be a good estimate. I was doing some soil survey, not surveying, but sampling over in Anniston, Alabama, which is a little bit east of us here. So I was using a magnetic compass. So I could say, this is close enough for me, okay? Because it's pretty close to me. But back in the old days, it's all they had, so they used it, okay? Now we have gyroscopic compasses that give you true north. So those are a little bit better. Now, here's the part I cannot explain at all. I can't even give you any really good educated guesses. But they, by studying, okay, why is some hematite really magnetite and some of it's just hematite. In other words, some iron ore is magnetized and some is not. Here is the best reason I can give, and this is just a guess. I think the Earth's magnetic field varies in time. It's sort of like temperature. We talked about that a little bit before too. Yeah, you have natural cycles of heating and cooling. I think for some reason the Earth's magnetic field does. There are some times when the field is at a maximum, and sometimes it's zero, and sometimes the field is at a minimum. Zero, maximum, zero. So there have been these times over time when the Earth's magnetic field has reversed itself. Now, I don't think there's anything cataclysmic or something like that that happens that makes it change. I think what happens is it slowly changes. And right now, I think we've been past the peak and we're getting weaker. Not going to zero yet, but it's probably going to be thousands or tens of thousands of years before we're going to reach that. For a while, the magnetic compasses aren't going to work. If my theory works, is that after a while they're going to point the opposite direction. So you just change the foot north. It's going the other way, and they get strong again, and they go weak. Because they found out, and this is in your text. Yeah. Is it time? How sad. Oh, just when we were there. Let's see if we can wrap this up. Yeah. Here's where we are at the bottom of page 157. Studies of rocks by geological dating and studies of frozen magnetic mineral orientation shows that the Earth's magnetic field has undergone, and they say sudden reversals. I don't think personally they're that sudden. I think they're very gradual over time, but reversals in polarity, north magnetic pole becomes south and vice versa. This has happened many times over distant geologic past. The most recent shift occurred 780,000 years ago. Now, how many of you were around then? Okay. Was man even around then? I don't think there's any record that we weren't. I think we've only been evidence on the planet for a few thousand years, okay? So the last one was then, and it's been several times. I mean, the Earth's been around, they think, about 12 billion years, okay? So yeah, it's had a bunch of shifts. We haven't been around to recognize it. The whole time we've been on the Earth is pointed to the real north. And probably the whole time we're going to be here, at least our generation, and the next several generations of generations, it's going to point north. But at some time, it may reverse itself again. Okay? We'll end on that slide and pick up next time with electric currents and magnetism. That's pretty good. That's 6.4, top of page 185. That's where we'll start next time. Okay, now y'all just talked me into a break, and here we're going to have another one. So sorry about that. I've got to get things shut down here. We'll be going. I'll go and give you your lab. I think I've placed them in here. If you go down to the lab, please don't mess with anything till I get there, okay? Oh my goodness, the 10 o'clock scholar. Okay. All right. Y'all can be reading the first few pages of the lab, but don't do anything until I get there, except read. And if some of the reading enables you to answer some questions, you can do that. Something else. Another two over here. Okay. So if y'all want to move on down toward the lab, you can. If you want to take a little break time, you can. It'll take me probably at least 5 minutes to get there, but get there as soon as you can, because the sooner we get it done, the sooner we can get out of here. Y'all can get out of here. Good deal, thanks. I'll be here till close to 8. Oh, I don't know such a thing. Or at least the people who pay me don't know such a thing. I have a high-tech pencil sharpener here. If you could
I haven't seen one of those in years.
Okay. I'm going to pause. Okay, we're ready to roll on the experiment. I hope y'all have read the first page, right? Ohm's law. You've noticed what voltage is, current is, amperage measures current, or amperage short, resistance. Ohm's law is written in 2 forms. You could do a third form if you wanted to. Okay. I've set up the lab to be like one thing I forgot to do. Check all these. Yeah. Okay. I set up, and you'll notice if you look at this, the setup I've done, you'll see here's your power supply acting like a battery. It's feeding out of it into the ammeter. We'll set it up for ammeter. And then from the ammeter over here across the resistor and back to the power supply. Now, you don't see a voltmeter here because that's what's measured on your window here. The voltmeter is inside here, so we didn't need a separate voltmeter. Okay. And what it says to, I've set it up that way, check it, make sure it's correct. You will adjust the DC adjustable power supply, okay, as instructed by me, okay? And here's what I suggest. Start with it at 1 volt. Okay, it's going to take a little time to get down there. It has a little bit of drift to it, so I'll let you set it for 1 volt. Turn it on, turn it down, and then turn it up. Okay, got it? Okay. Okay, here's probably what the problem is. That thing has been hit by mistake. Make sure the first blue button is depressed. That was what was wrong with theirs. Okay, good. All right. Then start it. Hey, y'all are working? Okay. Adjust your voltmeter to read 1 volt. Okay? And what I would suggest, okay, wait, let me set up your ammeter for you. You set it for 1 volt. While you do that, I'll set up. Did you set for 1? Okay. Okay, you're on your ammeter. You read DCA, and I've got mine on the 20 milliamp scale. Okay, is that where you are? Okay, I see nothing coming. Oh wait, turn it up to 1 volt. That's the simple. Okay. DCA, 20 milliamp. Do your own. And if it drifts, do 1.1. That's fine. Okay. What you do is go back to your table on page 197. There's 2 tables. Do it the first one. This is the known resistance. On page 197 with voltage V, as close as you can get to 1. This one says 0.9. That one says 1.1. This one says 1.0. Record the voltage. Record the current. Current is on the black box at the top. And this is in milliamps, so that would be, yeah, but what you need to do is record the current in amps. This is in milliamps. I'm just going to read theirs. I'm just going to round it to 7. That would be 7 milliamps would be 0.007 amps. Okay? Same thing you move it up 3 places to the left. That would give you your amps. Yeah. If yours is 9.9, then it'd be 0.0099. Okay. Now the voltages to shoot for are 1 volt, 2 volt, 3 volt, 4 volt, 5 volts, and 6 volts. Pretty simple. Down the column here, 1, 2, 3, 4, 5, 6. Now, again, if it's 0.9 or 1.9 or 2.1, that's fine. Get as close as you can. Record the voltage and then read the amp, but be sure you get it in amps, not milliamps.
So move it up to 2.
Move it up to 2. Once you've read the 1, move it as close as you can get to 2. Go forward.
Is it okay if we put 1.9?
That's fine. As
Oh,
close
it,
as you can
it,
get
it
to 2.
came up to 2.0.
Okay.
18.
We have to read it correct.
So we're at 2 volts.
Okay.
We got to move over 2 points.
And then we're at 17.
Okay.
What's it?
0.9.
No,
0.9.
yes, we don't add
It
it.
was
Because that's 1.
I thought it was 2.
So y'all do. Once you get all your data points, then stop and see me.
It's just going to be 2, so it's going to be 1.7.
So we will go with 19. Okay. 0, 1, 9.
17.
What's that?
On the 17, that one says 17.5 amps. Can I just put that as 18 milliamps?
No, I want you to record it in amps. What this says here,
So you don't amps.
I don't want that. So 17 is 0.175. Whatever. Is that what was answering your question?
Yeah.
Yeah. Yes. Okay, no. That means it's going off scale, so you don't need to go up to 200 milliamp scale. So that's only 34.5.
We moved 3, so it'd be 0.034.
Yes, exactly. When you go to 3, you're probably going to go off scale. When you go up to 200 milliamp.
27.5 milliamps. Wait, 0.017? So 27.5. Well, at this point now we move the decimal point 2 places, so it's going to be 0.27 or 0.275. No, because we moved up for sure. We moved 2 decimals now, not 3. 0.275. No, I moved up to 2.
0.0596. It's going the right way. It just jumped or something.
We were 20. We're 37.5.
So we're just measuring the current across from that resistor.
What's that?
We're just measuring the current across that resistor.
Yes, we are. That's what we do. Measuring the voltage across it and current through it. Okay, no. Okay. If y'all are through with the 6 observations, okay, then what I want you to do, oh, here it is. Okay. All right. If y'all are not through, go and finish. While you're sitting, let's turn off the thing so we don't burn out the resistors or anything else. Okay. And I would say also 0 so I don't use up the battery. Okay. Now, all right. So record the value of the resistor and the 6 values for the current and voltage. Now, you haven't recorded the value of the resistor yet. What I want you to do is go down to results 1, and it's make a graph of your 6 data points in data table 22.1. Hopefully that's the one you were using, right? Page 197. Okay. Make a graph of those, placing the current on the horizontal axis, voltage on the vertical axis. Now I want y'all to tell me, I know the voltage is basically 1 to 6, right? What were your currents? Give me from the lowest to the highest.
0.18, 90 to 0.056.
Okay, from about 8 to 50 something, right? If you just move your decimal over. Okay? Is that what most of you are getting something about like that? So you see, and they wanted the current on the horizontal axis. And your current has a greater range than your, well, no, what do you say? 0.8? Yeah, it's about the same. So you can set it up any way you want to. Okay? Let's see. Really doesn't matter. Okay? If you want to do it this way, that's perfectly fine. Current this way and voltage this way. Now your voltage, 1, 2, 3, 4, 5, 6, that would work. 1, 2, 3, 4, 5, 6, that would work too. So what I would suggest, if you set it up, portrait, isn't that what they call it? Okay. Huh? Okay. That's your highest. Okay. So you'll start with 0 here and 0.01 here. Yeah. 0.02, 0.03, 0.704, 0.05. Okay. You got the 0.07. Okay. Scratch that, folks. Sorry about it. Turn it this way. Landscape. Okay. And do 0, 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07, 0.08. That'll get them all on there. And then your voltage will be 1, 2, 3, 4, 5, 6. You won't need 7. Okay? You got it? Okay. Yeah, that will be 1 volt, 2 volts, 3 volts, 4, 5, 6. Okay? And your current 0.01, 0.02, 0.03. Okay. While y'all are scratching away. Okay. Wait just a second. I'll be right with you. Say that again. 1, 2, 3, 4, 5, 6. Okay. Watch your points.
Actually, your box, I didn't have to do that. 4.5.
So what about the turf? So this is my question. So 1.1 is here. That's okay. And then the currency is that.
Last, let's see, that's 0.09. 0.0890. Okay, that would be. Last one is 2,000.09.
0.89
So it'd be at the 1 volt line.
Is that? Okay. Oh, no, it's 0.00. That's down here. That's right here.
That's fine, it's
Don't have right
0.89.
first time.
Yeah.
It's 0.890.
0.00890. If you have questions, please ask. Okay. I'm going to be just saying this so it gets recorded. Okay. By the way, in this, one of my larger classes, my medium-sized class here, out of 17 students, I've received 2 and only 2 research papers. Only 2. You only got 2 weekends left, folks. Get your research papers in. Okay? Test 1, I've still got 2 people out who's not done, I'm sorry. Lab 1, 2 people have not turned in lab 1. Test 1, 1 person hasn't done test 1. Lab 2, 2 people haven't done lab 2. By the way, they aren't the same 2 people or 1 people, it varies, okay? Lab 3, 2, 3, 4, 5, 6, 7, 8 people haven't turned in. The majority of people, no, just under the majority. Lab 4, 1, 2 haven't turned in lab 4. Test 2, everybody turned them in. I hope I've turned them back to everybody. Lab 5, 1, 2, 3, 4, 5, 6, 7 haven't turned in lab 5. Lab 6, 1, 2, 3, 4, 5, 6 haven't turned in lab 6. Lab 7, 1, 2, 3, 4, 5, 6. 6 haven't turned in lab 7. Test 3. I think everybody's turned in test 3 now. I'll try to give those back to you today. Okay? I'm not going any further for right now until I get the other grades done. Oh, another 10 o'clock scholar here. Okay. Okay, Lacey. Okay, you'll have to get the first part from them. Okay.
Oh, Dr. Powell, this is a good graph.
What's that?
I think we got a good graph.
You got a good graph?
Yeah.
Did you get a flow? Okay. Let me, hold on just a second. All right. So, have all the teams done, okay, what you should have done so far is, all right, you've done A, make a graph of the 6 data points, placing the current on the horizontal axis, the voltage on the vertical axis. Calculate the slope. Did you calculate the slope? Okay, change of y over change of x. Let me see your graph. And you're a straight line. Oh, look at that. That's great. Okay, so what I would do is take the maximum here, change of y to change of voltage here, between the min and the max, and then take the change of it. Oh, you left off that one. By the way, use one straight line, don't do segments. Do the best fit as a straight line. Yeah, well, come as close as you can to as many dots as possible.
Also, you want us to come from zero.
Okay, and zero, if it looks like it's going to fit, I would put 0 in it too. But remember, you didn't measure 0, but because 0 volts is going to be 0 current, right? All right, so it's not bad to use 0, 0 also. Okay, once you've calculated or drawn your graph, then you pick the farthest 2 points apart that match as close as possible, and from those 2 points, take a change of your voltage divided by your change of amperage between those 2 points. So you'll do a subtraction. You can probably use the number from your data table if they're close enough, if they're right on the money. Okay? Okay, you're supposed to do one line, not segments of line. Draw one line that fits as many points as possible. That's all right. You don't have to erase. Just do the line on top of it. Because you erase your data points then. Okay? All right. You made your best?
Yeah.
Okay. That's your best straight line. That's a very good straight line. You're going to that point exactly and that point exactly, right? You can go back to your table. And then you change the voltages from this to that, so that's exactly 5 difference there. You change your current to this minus that, do that subtraction, and divide that difference by this difference, and then you can get your estimated. Huh? Well, that is change the voltage of the change of current, and it's going to divide over change the voltage.
Okay. It's not on the, it's not on the.
Okay, that's a good straight line. Looks like, yeah, I mean, okay, it looks like these points are right on the line, don't they? So I would take the difference between these two points, the voltage difference divided by the current How are y'all doing? Y'all calculated the slope yet? Get your slope. Okay. As soon as y'all have some slopes, come up and tell me what you think they are. I'll tell you how good you are. Or not.
Ohms, would that be in ohms?
Yes, it will be, because voltage divided by current is ohms. They're recording their current and resist and voltage and current on the second unknown, plotted the graph, and now are calculating the slope of that second graph. Calculating slopes of the second graph, change of vertical over change of horizontal. What's that? Do I get here in the morning? About 7:45.
So you're here at 7:45 every day?
No, every day. Tuesday and Thursday, but Monday and Wednesday. Supposed to leave at 2 Monday and Wednesday, but I'm never going to leave for 4:15. On Friday, I usually leave about noon. So I work more than 40. First we did was I get paid big bucks.
I just. That's April when I leave 7:45. I was like, man, all that long. That's longer than a work day.
Yeah, I'm cool with being at work 12 hours.
I think we actually use like a gas card or something on the school board.
Well, if you do the 3-day classes, you do get
Yeah.
Yeah. No, it's different from this.
Pretty good. Pretty good.
He was really calling out first,
Yeah.
but then that's kind of like unintentionally, unintentionally instigating. Like, not really, but yeah.
Yeah, yeah.
This be the equivalence of 9.59
divided by 2.
This might back.
The slope was what we got negative.
Okay.
It was, he said take the decimal off. So,
Yeah,
yeah.
5 minus 1. Is that what the two you used? Okay, I think you went the wrong way. It's 4 divided by the other.
And then what is it? So this is the same thing.
Okay, so,
Numbers not on.
30 is the same song. 20 something. Hey, that was a good one, man. That was a good one. I still love it. That's a good one. Yeah, we down to some of that.
Oh, well then, okay, maybe it is.
It's enough.
I was reading what you wrote.
What is the actual resistor?
What did you get? Yeah, that's all right. Yeah, so that's 8.5 minutes. Very good. Yeah, a lot better than that. Okay. Huh?
7:15 now.
Yeah. Thank you, Juan. Want to go to the other room? That was the last test, right?
Yes, sir.
What was the value of our unknown resistance?
390.
I need mine to Dr. Fowler.
90 ohms.
That's test 4.
Yeah.
So we got this one and test 5.
That's 5 would be 2. Wait.
Is there a reason to draw?
Usually we'll finish chapter 5, so it's Thursday. And we'll start chapter 8. And we'll probably finish chapter 8 and while okay. I need a calendar. Today is the 1st.
Today's the 1st.
And then next
Tuesday is the 6th.
yeah. And then we have the 13th and 15th.
Okay, so the 15th will take
That's the final. Okay. So today we have the second lab in electricity. Monday we'll have the EM lab. Okay, electromagnetic.
This or less lab.
No,
I did
we will start chapter 8 and then on Thursday of next week we have each will have test box. Okay. We may have lab. Then on this day, we'll finish chapter 8 and not have a lab unless we did do a lab that day. Okay, we'll do the chemistry lab one of those 2 days. And then on this day, we'll actually have test 6 and
final exam. But we're gonna finish pretty easy this day, but if you want to take the test 8 this day, test 6 this day, you can. And even if you want to take the final that day, you can. You're gonna have plenty of time to do it. Just, yeah, this is when it's scheduled. This is optional that day.
Is this gonna be like the sentence?
Okay. All right. You didn't have to do this one. It was fun to do because you got that's 117. No, 127 divided by 390. Whatever that is. Right?
I didn't get that. I did 4.
No, I'm sorry. I said 27. 27, not 21. 27 divided by 390.
27 divided by 390.
Okay. Okay, and then multiply by 100. Yeah, 6.9%. Very good. But that, you didn't have to do that. If you do it up here. This question says, explain how the two graphs demonstrate all the law.
That's
You're dividing voltage by amperage. In other words, you can think of it this way. The voltage is proportional to the amperage, and the constant proportionality is your resistance.
I don't know what section it is. I need my test though. From Tuesday.
What's that?
My test from Tuesday.
You want to take it now? Oh, okay. Here it is, and you take it in the classroom.
so. Hey, Tiffany, put 7% on your paper somewhere.
What's that?
No, M equals
Good deal. Thank you.
M equals
All right. Have a good weekend.
417 ohms, 417 ohms.
I'm sorry.
M equals 417 ohms.
And on your, that's what you calculated,
Right.
and the actual was 390.
390, right. And then the vote, okay.
Okay.
Ohms long. That's probably how everything turned out when I was correct.
Yeah, you got it.
Okay, you said that for the Ohms law thing is voltage divider.
What's that?
Explain how the two graphs.
Okay. What you did was divide the changes vertical, which was voltage change, of the horizontal change, which is amperage change. Volts divided by amps is anywhere on the grade book. Got it right there. Thank you. Oh, that was easy to knock out, wasn't it?
You did get my lab, right? I gave you
Okay. Right there on the book. Yeah.
oh, you sit on the book.
Yeah. No, the grade book. That is the grade book. Cleverly disguised.
There's a few books in there.
Yeah. That's what schools are all about, right?
Oh.
Okay, so we did, that's what we did, the voltage change, vertical, then we divide the amperage change horizontal, that's supposed to be resistance. Gotcha.
The other way to think of that is the voltage is proportional to current. That's what we're doing. Constant proportionality is resistance. And that's what you're doing. Thought you were grabbing hold of it like, don't take this from me. Okay. All right, thank you. All right, thank you so much. Whoops. What's that?
Have you graded the test yet?
Yes, I have. I just have it recorded on the blackboard.
That's fine.
Haven't.
I can wait.
No, that's fine. Here. Thank you.
I'm scared.
What? What's that?
Because it's like 30 degrees out there, but you ain't got no coat.
Don't tell me it's 30 degrees, is it?
I have hot flashes, so I don't need a coat.
Yeah, but right now, at night, you probably come up.
It's 49 degrees.
What's that?
It's 49.
49. Okay, good.
They just changed it. Now it's definitely 44 degrees right now.
44. Okay. Do you feel like the lab was worthwhile?
Yes, sir.
Good. Excellent. Good answer, by the way. You too. Thank you. Yes. On the grade book.
Great.
See it? That's it right there.
All right, have a good night.
You do